Imagine our civilization, a tiny fledgling species on a small rocky world. We've learned to harness the wind, split the atom, and capture the light from our parent star. But our appetite for energy grows with every passing moment, with every new city that lights up the night, with every supercomputer that crunches the numbers of the cosmos. Our planet, as generous as it has been, has its limits. The energy we derive from fossil fuels, from the very geology of our world, is just a fleeting snack. What if we could have the whole meal? What if we could capture not just the sliver of sunlight that happens to strike our planet, but all of it? This is the grand, audacious idea behind a Dyson sphere. The concept was popularized by the brilliant physicist and mathematician Freeman Dyson back in 1960. He wasn't imagining a single solid shell enclosing a star. That would be gravitationally unstable and honestly, a bit of an engineering nightmare. Instead, he envisioned a vast swarm of orbiting habitats or solar collectors, a cloud of independent structures flying in tight formation around a star. Think of it less like a giant bowling ball and more like a dense, intricate beehive, with each individual bee a power plant, a habitat, or a factory. This collection of objects would be so numerous that from a distance, they would effectively block out the star's light, creating a megastructure that captures nearly every single photon of energy the star produces. Why does this idea capture our imagination so profoundly? Because it represents a fundamental leap in what it means to be a civilization. It's the ultimate power-up. Right now, we are a planetary species, bound by the resources of Earth. A Dyson sphere would signal our transition to a stellar species, a culture that operates on the scale of its own solar system. The energy it would provide is almost beyond our comprehension. It would be an energy source that could power technologies we can only dream of today: interstellar travel, planetary-scale climate control, and simulations of entire universes. It's a vision of a future where energy is no longer a constraint, where the only limit is our own imagination. The Dyson sphere is more than just a science fiction trope. It's a thought experiment that forces us to think big, to look beyond our immediate problems, and consider the long-term trajectory of humanity. It asks a powerful question: what are the ultimate limits of technology? What can a species, given enough time and ingenuity, truly achieve? It's a benchmark for our own potential, a cosmic goalpost planted firmly in the future. As we gaze up at the stars, we see not just points of light, but cosmic power stations, waiting for someone with enough ambition to come and plug in. Our sun is a gigantic nuclear fusion reactor, a blazing furnace hanging in the void. Every second it converts about 4 million tons of matter into pure energy, radiating it out into space in all directions. The amount of energy is staggering. In a single second, the sun produces more energy than humanity has used in its entire history. Yet, here on Earth we only catch a tiny fraction of that output. Most of it, more than 99.9999999%, sails right past us, lost to the cold, empty darkness of interstellar space. It's like standing next to a bonfire on a freezing night but only letting a single spark land on you to keep warm. A Dyson sphere is our attempt to build a blanket around that bonfire. The fundamental principle is simple: capture that wasted energy. The individual components of a Dyson swarm would likely be massive solar collectors, essentially glorified solar panels, but on a scale we can barely imagine. Each collector would be a vast, thin sheet of light-absorbing material, perhaps miles across, designed to soak up sunlight and convert it into usable electricity. This electricity could then be transmitted wirelessly, using focused beams of microwaves or lasers, to other parts of the swarm, to habitats where people live, to factories where new components are built, or to massive engines that could move the entire structure. It's the ultimate solar power project. Think about the numbers for a moment. The total power output of the sun is about 384 yottawatts. A yottawatt is a trillion watts. That's a 384 followed by 24 zeros. Our current global energy consumption is around 20 terawatts, which is a 20 followed by just 12 zeros. A completed Dyson sphere would give us access to roughly 20 billion times more energy than we use today. This isn't just an upgrade, it's a redefinition of what's possible. With that kind of power, you could deconstruct an entire planet and reassemble it. You could power computers capable of simulating reality down to the subatomic level. You could send starships to other galaxies. Energy scarcity would become an archaic concept, a relic of a primitive past. So how would it work in practice? The swarm of collectors would orbit the star at a distance where they could efficiently capture sunlight without being incinerated. For a star like our Sun, this habitable zone for solar collectors would be somewhere around the orbit of Earth or Venus. Each collector would need its own station-keeping thrusters to maintain a stable orbit and avoid colliding with its neighbors. The whole system would be a dynamic, self-regulating dance of trillions of independent components, all working in concert to form a single, cohesive, energy-gathering machine. It's a symphony of orbital mechanics and energy conversion on a scale that dwarfs anything humanity has ever built. How do you measure the progress of a civilization? Is it by its art, its philosophy, or its technological prowess? In 1964, the Soviet astronomer Nikolai Kardashev proposed a different kind of measuring stick, one based on a civilization's ability to harness energy. He imagined a cosmic ladder of advancement, now known as the Kardashev scale. It's a way to classify hypothetical alien civilizations, and perhaps our own future selves, based on the sheer scale of their energy consumption. It's a report card for cosmic development, and right now, humanity is still in kindergarten. We haven't even made it to Type 1 on the scale. A Type 1 civilization is a planetary one. It has mastered the ability to use all the energy available on its home planet. This includes all the sunlight that strikes its surface, plus all the geothermal, wind, and tidal energy. It would have complete control over its planet's weather, geology, and biosphere. By some estimates, humanity is currently around a Type 0.7 on this scale, and we might reach full Type 1 status in a century or two. This is the first major step on the cosmic ladder, the moment a species becomes the true master of its own world. It's a monumental achievement, but in the grand scheme of things, it's just the beginning. The next rung up is a Type 2 civilization, and this is where the Dyson sphere comes in. A Type 2 civilization is a stellar one. It has moved beyond the limits of its home planet and can harness the entire energy output of its parent star. This is precisely what a Dyson sphere is designed to do. By building a megastructure around its star, a Type 2 civilization would have an energy budget billions of times greater than a Type 1 civilization. This level of power opens up possibilities that seem like magic to us today, such as manipulating the fabric of space-time or moving entire solar systems. This is the stage where a species truly secures its long-term survival against cosmic threats, and the scale doesn't stop there. A Type 3 civilization is galactic. It has learned to harness the energy output of its entire home galaxy. This would involve colonizing billions of star systems, perhaps building Dyson spheres around a significant fraction of them, and even tapping into the supermassive black hole at the galactic center. The energy available to a Type 3 civilization would be staggering, making a Type 2 civilization look as primitive as we look to them. They would be the true masters of the cosmos, beings of unimaginable power and scope. The Kardashev scale gives us a roadmap, a vision of what humanity could one day become if we survive and continue to explore. The idea of a Dyson sphere isn't pure fantasy, it rests on solid principles of physics that we understand today. The first and most important principle is the law of conservation of energy. Energy cannot be created or destroyed, only changed from one form to another. A star like our Sun is constantly converting its mass into energy in the form of light and heat. A Dyson sphere is simply a device designed to intercept that energy and convert it into a more useful form, like electricity. The science is sound, the challenge isn't in the what, but in the how. It's a problem of engineering, not physics. Another key scientific concept is orbital mechanics, the celestial ballet governed by gravity. We are already masters of this to a small degree. We place satellites in precise orbits around Earth, and we send probes on complex trajectories throughout the solar system. A Dyson swarm would be the ultimate expression of this mastery. Each of the trillions of components would need to be placed in a carefully calculated orbit, forming a stable, non-colliding pattern around the star. We would need to account for the gravitational pull of the star, the planets, and even the other components of the swarm itself. It would require a level of computational power and navigational precision far beyond anything we currently possess. Then there's the science of materials. What would you even build these collectors out of? They would need to be incredibly lightweight to be launched into orbit economically, yet strong enough to withstand the harsh environment of space. They would need to be highly efficient at absorbing sunlight and converting it to energy, and also excellent at radiating away waste heat. Any machine that processes energy is never 100% efficient. The leftover energy has to go somewhere, and in the vacuum of space, that means radiating it away as infrared light. This waste heat, in fact, is one of the key signatures we look for when searching for alien megastructures. Finally, we need to consider the transmission of power. It's not enough to just collect the energy, you have to get it to where it's needed. The most likely method would be wireless power transmission using highly focused beams of energy, probably microwaves or lasers. We've demonstrated this technology on a small scale here on Earth. A Dyson sphere would require doing it over millions of miles with incredible efficiency and precision. You would need to aim a beam of energy from a collector on one side of the solar system to a habitat on the other, without missing. The science is there, but the scale of the application is mind-boggling. Building a Dyson sphere would be, without exaggeration, the single largest engineering project in human history. The sheer scale of the undertaking is, honestly, difficult to wrap our minds around. Let's just consider the amount of material required. To build a swarm with enough collectors to cover the area of a sphere at Earth's orbit, you would need a mass equivalent to that of a large asteroid, or maybe even a small planet. Where would we get all that raw material? Launching it from Earth is completely out of the question. The cost in energy and resources would be, well, astronomical. We would have to become masters of space mining. The most logical source for these materials is the asteroid belt, or perhaps a planet like Mercury. We would need to develop fully automated mining operations, robotic factories that could devour entire asteroids, process their raw materials, and fabricate the components of the swarm. Think of self-replicating machines, sometimes called von Neumann probes. You would send a single seed factory to an asteroid, and its first job would be to build copies of itself. These new factories would then build more factories, and this kind of exponential growth would rapidly create an industrial base capable of producing the trillions of components needed for the sphere. It's a process that would likely take centuries, if not millennia. Then there's the problem of assembly. Once you have your trillions of solar collectors, habitats, and power relays, you have to put them all in the correct orbit around the sun. This is a logistical challenge of cosmic proportions. Each component would need to be launched from its construction site and navigated to its final destination with pinpoint accuracy. The entire solar system would become a construction zone, a complex web of flight paths and orbital insertions. A single miscalculation could lead to a catastrophic chain reaction of collisions, a cosmic game of billiards that could destroy decades of work in an instant. The coordination required would demand an advanced artificial intelligence to manage the chaos. And let's not forget maintenance. A structure made of trillions of moving parts, constantly bombarded by solar radiation and micrometeoroids, would require constant upkeep. We would need fleets of autonomous repair drones constantly patrolling the swarm, identifying damaged components and replacing them. The Dyson sphere wouldn't be a static object that you build once and forget about. It would be a living, dynamic system, constantly being repaired, upgraded, and expanded. It would be less like building a bridge and more like tending a garden the size of the solar system. The engineering challenges are immense, a true test for a species aspiring to a Type 2 status. So, what kind of materials would we need to build this colossal structure? Forget about steel and concrete, they are far too heavy and ill-suited for the task. We would need to turn to the cutting edge of material science, to substances that are currently being developed in our most advanced laboratories. The primary requirement would be a high strength-to-weight ratio. You want something incredibly strong but also incredibly light, so you can make vast structures without them collapsing under their own mass or costing too much energy to launch. Materials like carbon nanotubes or graphene come to mind. Graphene is a one-atom thick sheet of carbon atoms arranged in a honeycomb lattice. It's about 200 times stronger than steel, yet incredibly lightweight and an excellent conductor of electricity. You could imagine vast, gossamer sails of graphene coated with light-absorbing materials forming the primary collectors of the swarm. Carbon nanotubes, which are essentially rolled-up sheets of graphene, could provide the structural framework, the girders and cables holding everything together. These materials are still difficult and expensive to produce in large quantities today, but a future civilization with the resources of a solar system could likely manufacture them on an industrial scale. Another critical factor is heat resistance and radiation shielding. The components of the swarm would be bathed in the intense, unfiltered radiation of the sun. They would need to withstand high temperatures and a constant barrage of high-energy particles without degrading. Perhaps we would use advanced ceramics or composite materials, engineered at the molecular level to reflect harmful radiation and efficiently manage heat. For the habitats where people would live, the shielding would need to be even more robust, likely involving thick layers of rock, water, or specialized materials to protect biological life from the harshness of space. The ultimate source for all these building blocks would have to be space itself. As we've discussed, launching materials from a planet with significant gravity like Earth is wildly impractical. The most efficient plan would be to dismantle a planet that is rich in the necessary elements and close to the Sun. Mercury is a prime candidate. It's dense, rich in metals and silicates, and has a relatively low escape velocity. A Type II civilization could systematically deconstruct Mercury, asteroid by asteroid, and feed its mass into the orbiting factories that are building the sphere. It's a chilling and awe-inspiring thought, turning a planet into a power station. What would it be like to live in a civilization powered by a Dyson sphere? It would be a future fundamentally different from our own, a world where the limitations that define our lives have been erased. With a virtually infinite supply of energy, society could solve problems like poverty, hunger, and resource scarcity once and for all. The focus of civilization could shift from mere survival and competition to exploration, creativity, and the pursuit of knowledge. It would be a golden age for humanity, a time of unprecedented prosperity and potential. The very structure of society might change. Instead of living on the surface of a single planet, most of humanity might reside in countless orbiting habitats within the swarm. Each habitat could be its own self-contained world, a spinning cylinder or torus generating artificial gravity through rotation. You could have habitats that simulate any environment from Earth's history, from lush rainforests to frozen tundras. You could have worlds dedicated entirely to art, to science, or to recreation. With the energy of a star at your command, you could build paradise, not just once but millions of times over. The concept of a home planet might fade away, replaced by a home system. With near limitless computational power, the line between reality and simulation could begin to blur. We could create virtual worlds so detailed and realistic that they are indistinguishable from the physical world. These ancestor simulations could allow us to perfectly recreate historical events or explore alternate timelines. We could upload consciousness, allowing individuals to live on indefinitely in digital form, exploring virtual universes of their own creation. The very nature of identity and existence would be called into question when your mind can be copied, backed up, and transferred from a biological body to a digital substrate. This future also presents new philosophical and ethical dilemmas. What is the purpose of a civilization that has conquered all its physical challenges? When you have the power of a god, how do you wield it wisely? A Type II civilization would face questions on a scale we can barely comprehend. Should they interfere with the development of younger, less advanced species? Should they embark on projects to re-engineer the galaxy itself? The transition to a Type II civilization isn't just an engineering challenge, it's a test of our species' maturity and wisdom. It's the moment we graduate from being children of Earth to becoming adults of the cosmos. If a Type II civilization is a plausible step in the evolution of intelligent life, then perhaps there are already some out there. So how would we find them? A completed Dyson sphere would be very difficult to see in visible light, as it would block most of its star's output. From our perspective, a star might seem to dim or even vanish completely from the sky, but the laws of thermodynamics offer us a clue. As we discussed, any machine that uses energy generates waste heat. A Dyson sphere, even a highly efficient one, would be no exception. This waste heat would have to be radiated away into space, most likely in the form of infrared radiation. So a key way to search for Dyson spheres is to look for objects that are unusually bright in the infrared spectrum, but dim or invisible in the visible spectrum. We would be looking for a large, warm object with a temperature of a few hundred degrees, glowing faintly in the dark. It would be a celestial object with no good natural explanation. Our infrared telescopes, like the James Webb Space Telescope, are our best tools for this search. They scan the skies for these strange, warm shadows, these potential calling cards of advanced alien engineers. Several searches have already been conducted, combing through data from infrared sky surveys. One of the most famous examples was the star Kaisi 8462852, also known as Tabby's star. This star showed strange, irregular dips in its brightness, with its light dimming by as much as 22%. A swarm of alien megastructures was one of the more exotic hypotheses proposed to explain this bizarre behavior. While further observation suggested that the dimming was more likely caused by a cloud of cosmic dust, the excitement it generated showed how seriously the scientific community takes the search for these techno-signatures. Finding a Dyson sphere would be one of the most profound discoveries in the history of science. It would be definitive proof that we are not alone in the universe. It would also give us a glimpse of our own possible future. It would tell us that it's possible for a civilization to survive its technological infancy, to overcome the challenges of its home world, and to make the leap to a stellar scale. It would be a message of hope, an affirmation that the path to the stars is open. The silence of the cosmos is vast, but with every new telescope and every new survey, we are listening more closely for the faint, warm whisper of a distant, industrious neighbor. The journey of life on Earth is a story of increasing complexity and capability. From single-celled organisms to intelligent primates, life has constantly found new ways to harness energy and reshape its environment. We, humanity, are the current pinnacle of that process on this planet. We are the universe made aware of itself. We are stardust, animated and organized, now looking back at the stars from which we came and contemplating our next move. The concept of a Dyson sphere in this context feels less like a wild science fiction fantasy and more like a natural, logical next step in our cosmic evolution. Building such a structure would represent the ultimate triumph of intelligence over the raw, untamed forces of nature. It would be the moment our species transitions from being passive inhabitants of the universe to active architects of our own destiny. We would no longer be at the mercy of planetary catastrophes or the slow, inevitable death of our sun. We would have the power and the resources to ensure the survival and prosperity of our civilization for millions, perhaps billions of years. It would be the ultimate life insurance policy for humanity, securing our legacy among the stars. This grand vision forces us to confront some of the deepest questions about our place in the cosmos. Are we destined to remain confined to this single, fragile planet, or is our destiny written in the stars? Do we have the courage, the ingenuity, and the long-term vision to embark on a project that will not be completed in our lifetimes, or even in the lifetimes of our great-great-grandchildren? It's a project that would require a level of cooperation and unity that our species has never before achieved. To build a Dyson sphere, we must first overcome our tribal instincts and learn to think as a single planetary species with a shared future. So, is the Dyson sphere science fiction or future reality? Right now it is firmly in the realm of science fiction, but the science behind it is real, and the path forward, while incredibly challenging, is not impossible. It is a vision that pulls us forward, that inspires us to dream bigger and to reach higher. Perhaps one day, in the distant future, our descendants will look out from their orbiting homes, not at a single point of light in the sky, but at the magnificent, glowing architecture of their own creation, a testament to the species that rose from the dust of a small blue planet to become the builders of stars. That is a destiny worth striving for.